project called ThunderML, which we have been developing in the last 2 years, and we will still need 1 to 2 years to continue to complete this project. It's about machine learning systems which can run on heterogeneous architectures such as CPUs and GPUs. It can be used potentially anywhere in the database systems where require the AI techniques. Today, machine learning has been very popular, and the popularity of machine learning is largely due to the easy-to-use systems such as TensorFlow for the deep learning-based techniques, scikit-learn for the conventional machine learning-based techniques. However, building machine learning techniques, building a good machine learning models can be slow. For example, if we want to learn an index, given these problems, first we need to decide which machine learning algorithm we need to use. After we make the decision, we need to tune the hyperparameters of the corresponding algorithms, and this process can be very time consuming. And even the training process itself can be very slow, especially for large data sets. So more concretely, I run an experiment in the following settings. We run the data set has about 8 million training instances, and each instance has about 800 dimensions. This experiment was run on a relatively high-end workstation. The tool is called libHVM. The training process took about 9 days. The library we built called ThunderHVM, it can complete the task in just 2 hours on a common GPUs. And as you can see, by using the hardware more efficiently, we can achieve a significant speed up. So next I will talk about the 2 projects in our ThunderML system. The first one is ThunderHVM, and the second one is ThunderGPM. And finally, I will conclude the talk and also present an overview of our ThunderML system. So some of you may have already known what HVM is. The full name is called support vector machines. This model actually is very powerful for the tabular data, or you have a small data sets or the medium data sets, and it's very useful. So the goal is to find a hyperplane that can separate the two classes of data points with the maximum margin. The most popular algorithm for training HVM is called the sequential minimum optimization algorithm, or SMO for short. In the community, there are many studies try to accelerate these SMO algorithms using GPUs, but they have some limitations. First, in each iteration, they require synchronization, and in each iteration, they only handle 2 training instances and use these 2 training instances to update the hyperplane. But it's inefficient in GPU because we have so many computation resources, and each time we only consider 2 of the training data is quite inefficient. So our key idea is that instead of using 2 instances, we use 2 sets of instances, and then we can address the hyperplane of the HVM in a batch processing manner. So this is the key idea. But exploring these intuitions have some challenges as well. For example, when we set the batch size, if the batch size is very small, then the efficiency of the library could be similar to the original SMO. However, if the batch size is too large, we may end up running out of the GPU memory. And the second challenge is that we may end up having local optimization problems, because now we are considering a batch of the instances, and it's likely that we could stuck into the local optimization. Intuitively, we may not moving in the right direction. So in the end, we may have a slower algorithm. So our key ideas of tackling these challenges includes the first one is we propose the data-aware technique. The key intuition is that we take the computation resources of a particular GPU and also the problem size, and then to figure out a reasonable batch size automatically. To tackle the second challenge, we exploit the shared memory of the GPU such that we can put the key information of the batch into the shared memory and to improve the efficiency of per iteration. We also propose some mechanism to mitigate the local optimizations, and more technical details are available in our papers. In the ThunderML project, we have performed system abstractions such that we can support more functionalities while keeping the systems simple. SVM is a very powerful tool, and it can be used for regression tasks, can be used for classification tasks, and also the one-class problems. And all these problems can be solved by the parallel SMO solver that I presented previously. Okay, this slide shows some key results of our ThunderML project in comparison with the existing tool. In terms of training, our library is about 10 to 100 times faster. In terms of prediction, we can achieve 100 times speed up. The model produced by our system is identical to that of the existing one. This slide shows some key outcomes of our ThunderML project so far. It's open source on GitHub. We have attracted more than 1,000 stars and more than 140 folks. Every month we have about 2,000 unique visitors to the repository, but we expect the users of the repository is much larger, because many users just download the code and then use it for many times, which we cannot track. We have also published some papers about this project. If you are interested, you can take a look. Now I go to the second project called ThunderGBIM, which is a fast training algorithm for the gradient boosting decision trees on GPUs. The full name, the short name for gradient boosting decision tree is called GBDT. This algorithm actually is also very popular, particularly for the tabular data. It's easy to use, and also it has the capability to win many data mining and machine learning competitions. When we are designing the GPU-based algorithm for these GBDTs, we also face a lot of challenges. The first challenge is that there are many irregular memory accesses. As you can imagine, due to the tree structures, the data could go to the left branch or go to the right branch, depending on the internal node. The second challenge is that the intermediate result it is much larger than the GPU memory, especially for the large data sets. And the third challenge is that training the high-dimensional problems can be very expensive, because for each dimension we need to find the best split points and then to pick out the best dimension. So we propose various kinds of techniques to tackle each of these challenges. For example, we propose the data preserving data partitioning. So once we split one node into two nodes, the data in the two child nodes are naturally sorted. We also propose compression, approximation, and also multi-GPU supports in order to handle bigger and more complex problems. And we developed the so-called attribute-based data partitioning such that the communications between threads and between GPUs can be minimized. So we also conduct experiments to compare our system against the existing ones. So when we compare our library with the existing systems on GPUs, our system is is faster and also more scalable. When we compare the existing systems running on CPUs, we achieve around 10 times speed up. Again, the model produced by our system is identical to that of XGBoost, which is arguably the most popular library for GPT training. We also have the prediction module. It's around 5 times faster compared to the existing ones. This is some key outcomes of the ThunderGPM project so far. It's also open source on GitHub. We have more than 400 stars and more than 50 forks. Every month we have around 1,000 unique registers. Sorry, I think the URL is incorrect. So it should be ThunderGPM, not GVM. So we have also published 2 papers, and the other paper is currently under review. This figure shows the key infrastructure of our ThunderML project. So at the bottom, we have the computation devices, including GPUs and CPU. And then we have the programming framework. And we aim to develop a set of primitives which can support different kinds of machine learning algorithms, such as SVM, GPTs, etc. And then we have a layer for the hyperparameter tuning and algorithm selections. And on top of that, we have the automatic feature engineering layer, such that users can use our system in an end-to-end manner. And then we have the users can run their own applications, such as document classification, sales forecasting, etc. In conclusions, I have briefly talked about the importance of machine learning systems and also demonstrate that the HBM training process can be speed up by 10 to 100 times. The GPT training can be accelerated by 10 times using GPUs with our techniques. And also our Thunder HBM and Thunder GPM projects of this bigger system, the bigger system called ThunderML, have attracted a large number of users. With that, I conclude my talk, and thank you.
Any questions?
So is that, when you say it's faster inference time, is that including the round trip to the GPU?
Yes.
So a GPU round trip is like 7,000 nanoseconds. What's wrong with these SVM libraries? Like, why do they need more than 50 cache misses to do inference?
You mean why the existing system is slower?
I mean, like, it takes you a certain amount of time to go from the host memory to the GPU, right? And that's huge. It's like 7,000 nanoseconds.
Yeah.
What are these other libraries doing that they're not finishing inference?
Yeah, actually in the